A single stone can outweigh 200 elephants. This is the staggering reality of the monumental quarrying techniques that shaped our ancient world. How did civilizations without cranes or engines extract and move 1,000-ton blocks from the living earth? By the end of this exploration, you will understand the precise, brilliant methods that turned geological wisdom into eternal stone. We will uncover how fire and water could fracture granite, and how wooden wedges lifted by water alone split mountains. What forgotten knowledge allowed builders to orchestrate such feats, and why does so much of their skill feel lost to time? When you look at these silent stone giants, what do you believe human determination is truly capable of achieving? 1,000 tons is a number that slides past our understanding. To grasp it, you must step away from the abstract and into the tangible world. Think of a fully grown African elephant, a creature whose very presence seems to shake the ground. Now picture 200 of them standing shoulder to shoulder, a living, breathing mountain of muscle and bone. That is the weight of a single block of stone. Or imagine an entire parking lot filled with 160 family cars, every sedan and minivan compacted into a single, silent slab of granite. This is the physical reality ancient quarry masters faced. They were not moving boulders, they were relocating geological formations. We have tangible examples that anchor this scale in reality. In Egypt, at the ancient granite quarries of Aswan, there lies the unfinished obelisk, still partially attached to the bedrock. This colossal shaft would have measured over 100 feet long if completed, with an estimated weight of 1,200 tons. It is a frozen moment of ambition, showing us exactly what they intended to lift. Across the Mediterranean, in the ruins of Baalbek, Lebanon, sit the Trilithon stones. 3 limestone blocks, each roughly 64 feet long, 14 feet high, and 12 feet deep, form a foundation wall so immense it defies belief. Each one weighs approximately 800 tons. To stand before them is to feel a profound shift in perspective, a humbling realization of what human hands, guided by an ingenious mind, can achieve. This was the monumental challenge. It was not merely a matter of strength, but of physics, logistics, and profound patience. Every decision, from the moment the stone was selected in the quarry to its final placement, was dictated by this unimaginable mass. How do you even begin to cut such a thing free? How do you transport it without crushing the very road beneath it? How do you lift it with perfect precision into a waiting wall? The solutions could not be brute force. They had to be elegant, leveraging natural laws in ways we are only now beginning to fully appreciate. To solve a puzzle of this magnitude, you first have to respect the sheer weight of the problem. The rock itself held the first secret. Before any tool ever touched the stone, ancient engineers engaged in a deep, silent dialogue with the landscape. They were not merely quarrymen, they were master geologists, reading the Earth's own manuscript written in layers of sediment and fractures. Their first and most critical principle was site selection, a process that blended keen observation with generations of accumulated wisdom. They sought more than just a specific type of stone, like the iconic pink granite of Aswan or the dense limestone of Baalbek. They were searching for the perfect bed within that stone, a geological sweet spot where nature had already done much of the preparatory work. What they looked for were natural planes of weakness called joints. These are the cracks that form in all rock masses as they cool, contract, and settle over eons. A skilled eye could trace these joints, seeing where a 1,000-ton block was already partially defined by the planet itself. At the Aswan quarries, the granite is renowned for its remarkable uniformity, a crystalline mass relatively free of the internal flaws that could shatter a block during extraction. Choosing to work here along these natural partings was a strategic decision that reduced the initial labor by orders of magnitude. Instead of fighting the mountain, they collaborated with it. This foundational step of listening to the rock, of understanding its grain and its temperament, determined the entire project's feasibility. A mistake here meant months of wasted effort or a catastrophic failure deep within the quarry. Their success began not with force but with perception, seeing the latent form within the solid earth. This geological wisdom was the silent partner in every operation that followed. With a perfect block chosen by its natural partings, the real work of creation could begin. This was the moment of commitment, when an abstract vision had to be etched irrevocably onto the face of the earth. The second principle was the art of delineation, the meticulous process of marking the monolith's exact shape onto the unyielding bedrock. This was far more than simple chalk marking. It was the ancient world's equivalent of a master architect unrolling a full-scale blueprint, except this blueprint was painted or carved directly onto a mountainside. Evidence from quarries across the world suggests a variety of precise methods. Teams likely used painted lines made from ochre or other natural pigments to lay out the initial, complex shapes of obelisks or column drums. For more permanent guides, they employed shallow grooves, patiently chiseled with tools made of even harder stone like dolerite. In some cases, they may have used fire-hardened wooden templates, pressing them into the rock dust to leave a perfect negative outline. The proof of this exacting process is still visible today. At the site of the unfinished obelisk in Aswan, you can walk around the clearly defined trenches that were cut to isolate the giant shaft. These trenches are not rough or haphazard. They are precise, straight-edged and deep, showing that every angle and dimension was calculated and committed to the stone long before the monumental task of undercutting began. This delineation phase was a critical act of foresight. It forced the engineers to solve every logistical problem on a small scale first. They had to decide the block's final orientation, how to manage its center of gravity, and exactly where to begin the delicate work of separation. A mistake in the marking would become a catastrophic 1,000-ton flaw. This step transformed the mountain from a passive source of material into an active participant in a grand design. The lines on the rock were a promise, a declaration of intent to the stone itself. Once those lines were set, there was no turning back. The mountain had been marked, its fate outlined in paint and groove. But the granite itself remained an unbroken whole, a sleeping giant bound to the earth. To awaken it, to convince it to part from the bedrock, required a kind of elemental persuasion. This leads us to the third and perhaps most ingenious technique, the leverage of natural forces through thermal shock. It is a method that feels almost like alchemy, turning fire and water into a precision tool capable of splitting the hardest stone. Think of a glass baking dish taken straight from a hot oven. If you were to run cold water over it, the sudden, drastic change in temperature would likely cause it to crack or shatter. This is thermal shock in its most basic form. Different materials expand when heated and contract when cooled, and doing this too rapidly creates immense internal stress. Ancient quarry masters applied this principle on a monumental scale. The process was deceptively simple, yet required profound control. Along the carefully delineated line meant to become the block's edge, workers would build a controlled fire, often using readily available brushwood. They would let this fire burn for hours, sometimes even days, patiently heating the surface of the granite or basalt to a high temperature. The stone would expand, but only at the surface. Then, at the critical moment, they would douse the superheated rock with a sudden deluge of cold water. Some historical accounts even suggest the use of vinegar, which could potentially create a more violent reaction. The surface layer, now cooled and contracted in an instant, would pull away from the still hot interior. This differential stress created a network of microfractures, a spiderweb of weakness along a perfectly straight plane. The rock, in essence, began to split itself. Evidence for this technique is found in tool marks and the very character of ancient quarries. In many sites, you can see long, remarkably straight trenches that seem too precise to have been pounded out solely with stone hammers. The surfaces sometimes bear a characteristic spalling or flaking, consistent with rapid heating and cooling. Furthermore, this method explains how they could work with incredibly hard stones like granite with what appears to be relative efficiency. It was not about overwhelming the stone with brute force, but about outthinking it. By harnessing the fundamental physics of expansion and contraction, they turned the rock's own properties against it. The fire and water did the deep, laborious work of initiating a fracture, a task that would have taken an army of workers weeks with simple tools. After the thermal shock did its work, teams could then move in with their dolerite pounders and copper chisels to widen the crack, insert wooden wedges, and finally coax the block free. It was a symphony of natural forces conducted with patience and deep understanding. This was not magic, but applied science of the highest order, a quiet dialogue with the elements that allowed them to ask the mountain for a piece of itself and receive an answer. The stone was now a sleeping giant, coaxed from its bed by fire and water. But the work of separation was not yet complete. A hairline fracture needed to become a clean break, and for this, ancient engineers employed a fourth, remarkably patient technique, the silent power of wooden wedges. This method represents a brilliant application of sustained, incremental force, a testament to understanding that slow persuasion can be more powerful than a sudden blow. Across the globe, from the granite quarries of Egypt to the volcanic slopes of Easter Island, the evidence is etched into the stone itself, narrow, rectangular slots cut in precise lines. These are the homes where wooden wedges once waited to perform their quiet miracle. The process was methodical. After using thermal shock or simple chiseling to create a starter crack along the desired plane, workers would carve a series of these slots at regular intervals. Into each slot, they would hammer a carefully shaped wedge made of dry, hard wood, likely oak or acacia. The wedges would be seated firmly but not driven in with overwhelming force. Then came the catalyst, water. Buckets would be poured over the line of wedges, saturating the dry wood. As the fibers absorbed the moisture, they began to swell, expanding with a relentless hydraulic pressure that could reach several tons per square inch. This was not an explosion, but a slow, irresistible push. Over hours or even days, the expanding wood acted like a distributed hydraulic jack, each wedge transferring its immense force directly into the heart of the stone. The pressure would build uniformly along the entire fracture line, guiding the rock to split with astonishing precision along the predetermined plane. The genius of this technique lies in its elegant use of natural material properties. The wood's expansion provided a force far greater than any human team could generate with hammers, and it did so steadily and controllably. It turned a simple, organic material into a precision tool for monumental engineering. On Easter Island, these wedge slots are clearly visible around the bases of the famous Moai statues, showing exactly how the islanders separated their colossal figures from the volcanic tuff of the Rono-Raraku quarry. In Aswan, similar markings can be found. This was not a secret known to one culture. It was a widespread solution to a universal problem, born from observing the world and applying its lessons with profound patience. The wedge did not conquer the stone through violence, but through persistent, intelligent pressure, a lesson in the power of gradual, focused effort over raw, immediate strength. With the block finally free, a new and even more daunting challenge emerged, one that required moving a small mountain. The block now lay defined, a sleeping giant outlined by fracture lines. But it was still one with the mountain, held fast on its underside by an unbroken connection to the bedrock. Freeing it completely required the fifth technique, a monumental exercise in patience and precision known as channeling and trench excavation. This was the process of digging the block's grave, only to resurrect it as a monument. The goal was simple in concept but staggering in execution: to carve a deep, narrow moat around the entire perimeter of the 1,000-ton stone, isolating it on all sides until only its base remained attached. The tools for this Herculean task were rudimentary by our standards, yet perfectly adapted to the work. Teams of laborers would use heavy, fist-sized balls of dolerite, a stone even harder than granite, to pound relentlessly at the bedrock. Each strike would crush a tiny amount of crystalline material into dust. Others would work with copper chisels, likely softened by the constant hammering and requiring frequent reshaping, to pry and chip along defined lines. This was not a rapid process. It was an act of geological erosion conducted by human hands, a symphony of countless tiny impacts played out over months or even years. The evidence of this meticulous work surrounds the unfinished obelisk in Aswan like a negative silhouette. You can walk through the trenches that were cut to free it, channels that are often only as wide as a person's shoulders. Their walls are remarkably vertical and smooth, a testament to the extraordinary control the workers maintained. Every swing of the dolerite pounder had to be measured. A strike too deep on one side could create a weak point that might cause the entire monolith to crack under its own weight later. A misaligned trench could mean the block became physically trapped, unable to be lifted or moved, rendering years of labor utterly worthless. This phase of the work was a silent, dusty, and grueling testament to human endurance. There was no shortcut, no clever trick of physics to speed it along, just the steady, rhythmic percussion of stone on stone, day after day, until the block stood alone on a slender pedestal of untouched rock. This trench was more than just a hole in the ground. It was the literal and figurative groundwork for everything that followed, the creation of a space from which the impossible weight could finally be lifted. Freeing the stone was only half the battle. Now came a delicate balancing act of almost unimaginable consequence. With the block isolated in its deep trench, perched on a slender pedestal of untouched rock, the engineers faced their most nerve-wracking moment. The monolith's own colossal weight, the very reason for its existence, now became its greatest threat. 1,000 tons of granite, if unsupported even for an instant, could fracture under its own immense pressure, shattering years of labor into a million worthless pieces. This was the logistical puzzle of underlying support, a problem solved not with force, but with foresight and a brilliant understanding of structural integrity. The solution was a masterstroke of practical engineering, the strategic use of temporary keystones. Before the final cuts were made, workers would intentionally leave several thick pillars of solid bedrock beneath the block. These were not accidental leftovers, they were carefully planned load-bearing supports, distributed to carry the stone's weight evenly. Think of a grand piano suspended on a few sturdy wooden blocks, each one placed precisely to prevent the instrument from sagging or collapsing. The ancient quarry masters were doing the same thing, but with a slab of stone heavier than a blue whale. These keystones acted as a natural, fail-safe cradle. They allowed the workers to methodically undercut the rest of the pedestal, preparing the block for its eventual journey, while the monolith itself remained perfectly stable, held aloft by the unyielding earth. The final act of extraction was a carefully orchestrated sequence. Only when everything else was ready, when the transport pathway was prepared and the lifting apparatus was in place, would teams return to those final pillars. Then, with painstaking care, they would chip away the last connections. It was a moment of supreme tension where the entire project hinged on the accuracy of their calculations. If the keystones were placed incorrectly, the stone would twist and crack. If they were removed out of sequence, the weight would shift catastrophically. This practice reveals an advanced, almost intuitive grasp of load distribution. They understood that the stone's strength had limits, and that those limits had to be respected until the very last second. The evidence for this is subtle but compelling. In quarries, archaeologists sometimes find the negative spaces where these pillars once stood, their surfaces showing the final, precise chisel marks of removal. It speaks to a philosophy that valued control over speed and preservation over haste. The keystone method was the ultimate safety measure, a patient hand ensuring the sleeping giant would awaken intact. With the block finally separated, resting securely on a prepared bed of sand or timber, the next monumental question demanded an answer. How do you persuade a small mountain to begin walking? The sleeping giant was now awake and free, but it was still trapped in the bottom of its own stone cradle. Detaching the block was a triumph of patience, yet it created a new and equally daunting problem. The monolith rested several feet below the surrounding ground level, at the bottom of the trench that had been carved around it. Before it could travel a single inch, it had to be lifted out of this pit and onto a level transport path. This critical maneuver, the transition from a static stone to a mobile object, was a pivotal moment of applied physics and coordinated effort. They could not simply pull it out, for the friction would be insurmountable. They could not dig a ramp down to it, as that would undermine the quarry walls. Their solution was a brilliant exercise in incremental elevation, a technique often called cribbing. Imagine trying to lift a grand piano a few inches off the ground by yourself. You couldn't simply pick it up, but if you had a stack of sturdy wooden blocks, you could use a lever to lift one corner just enough to slide a block underneath. Then you'd move to the next corner, repeat the process, and slowly, methodically, you would raise the entire piano onto a stable platform. Ancient engineers applied this exact principle, but their piano weighed 1,000 tons. The materials were simple, robust timber logs and strong wooden levers. The process began by carefully levering one end of the colossal block, using the stone's own mass as a fulcrum. The movement would be minuscule, perhaps only an inch or two, but in that tiny gap, workers would swiftly insert a crib, a short, sturdy stack of squared timber. They would then release the lever, allowing the stone to settle onto this new, slightly higher support. The team would then move to the opposite end and repeat the sequence, levering, cribbing, and settling. Over days or weeks, through thousands of these tiny, careful adjustments, the block would literally be walked upward, step by wooden step, out of its quarry bed. It was a physical symphony where every participant had to move in perfect harmony, a slow-motion dance guided by the rhythm of shouted commands. The sound would have been a chorus of creaking timber, the grunt of straining levers, and the solid thud as the stone settled onto its latest cradle. This cribbing technique transformed an impossible vertical lift into a manageable series of horizontal shifts. Each new layer of timber not only raised the stone but also created a stable, level surface from which the next phase could begin. Once the block was raised to the height of the quarry floor, the timber cribs could be reconfigured into a temporary road, a smooth runway leading toward the wider world. This launch phase was where theory met practice, where the abstract plans etched in stone became a living, groaning, moving reality. It proved that the true secret to moving mountains was not a single magical trick, but a chain of intelligent, patient solutions. With the stone finally poised on the brink of its journey, the next question became the most epic of all. How do you convince 1,000 tons of granite to glide across the landscape? The stone stood poised at the edge of its cradle, a leviathan ready for its journey. To move it, ancient engineers performed a breathtaking act of landscape architecture, constructing temporary mountains to conquer gravity itself. The most compelling answer to the question of horizontal transport is the monumental ramp, a sloping path of least resistance that transformed impossible inclines into manageable journeys. This was not a simple dirt pile, but a carefully engineered earthen highway, built with the same strategic foresight as the stonework it served. Imagine the logistics of building a ramp capable of supporting a 1,000-ton block. It would have required an army of laborers moving staggering volumes of soil, rubble, and stone, compacting it layer by layer into a stable, rising causeway. The ramp's angle was everything, a precise calculation balancing the need for a gentle slope against the sheer volume of material required. Too steep, and the block would become an uncontrollable avalanche. Too shallow, and the ramp would stretch for miles, becoming a project rivaling the final monument itself. At sites like the Great Pyramid of Giza, though the specific ramp design remains debated, the concept is undeniable. The construction of such an earthwork was a feat of civil engineering that rivaled the placement of the stones it carried, a temporary landscape created solely to serve a permanent legacy. This massive, sloping road was the ancient world's version of a dedicated freight corridor, a testament to the understanding that sometimes the most direct path to a goal is to reshape the very ground beneath your feet. But a ramp alone was not enough. A block of that mass would simply sink into the soil or grind to a halt from sheer friction. The true ingenuity lay in the surface treatment, turning a dirt road into a slick, low-friction track. Workers would often lubricate the ramp's surface with water or a slick slurry of wet clay. This simple mixture acted as a natural hydraulic fluid, drastically reducing the coefficient of friction between the stone's base and the earthen path. On a smaller scale, we can see this principle in action. Picture a heavy piece of furniture on a wooden floor. Pushing it dry is a struggle, but add a few drops of liquid soap or a damp cloth underneath, and it slides with surprising ease. The ancients scaled this basic physics lesson to a monumental degree. The block, now resting on a bed of timber sledges, could be pulled by teams of workers or oxen along this slickened path, the lubricant allowing the immense weight to be distributed and overcome. The synchronized pull of hundreds of ropes, the steady flow of water carriers maintaining the slurry, the shouted chants keeping rhythm, this was the symphony of movement. The ramp was more than just a structure, it was a dynamic system, a carefully managed environment where soil, water, wood, and human effort combined to achieve the seemingly effortless glide of geology itself. It represents a profound truth about these ancient projects. The permanent stone marvels we admire today are only half the story. The other half lies in the vanished landscapes of earth and labor, the temporary mountains built and then erased, all to deliver a single, silent message from the quarry to the sky. While ramps conquered vertical distance, the true test of ingenuity unfolded on the vast, flat plains between quarry and construction site. Here, the challenge was not elevation but friction, the immense, grinding resistance that tries to hold any massive object in place. The solution, refined over centuries, was a masterpiece of mechanical simplicity, the sled and roller system. This method transformed a static block into a mobile monument through coordinated motion. At its heart was a massive wooden sledge, a platform hewn from robust timbers, upon which the stone would be carefully levered and secured with ropes. This sledge did not slide directly on the ground, for that would have been an impossible task. Instead, it glided over a path of cylindrical rollers, logs of uniform diameter laid perpendicular to the direction of travel. The physics at play are elegant. As the sledge moves forward, it rolls over the logs beneath it. The friction encountered is rolling friction, which is dramatically lower than the sliding friction of dragging the sledge on bare earth. It is the difference between pushing a heavy box across a carpet and placing that same box on a set of rolling pins. The reduction in effort is profound. Egyptian tomb paintings, such as those at the tomb of Jehuti-Hotep, provide direct visual evidence of this system in action. They depict a colossal alabaster statue being transported on a sledge, pulled by long ropes by a large team of workers, with a figure standing at the front of the sledge pouring what is likely water or a lubricant onto the track ahead. The coordination required for this operation was a feat of logistics equal to the engineering. Imagine the scene, a 1,000-ton block on its sledge, inching forward. As it rolls onto the first set of logs, teams of workers at the rear must be ready. The moment a roller is cleared at the back, it is quickly carried around to the front and placed back into the path. This created a continuous moving track, a conveyor belt of wood laid down just ahead of the advancing stone. The rhythm had to be perfect, a synchronized dance of lifting, carrying, and placing, all while the main pulling teams maintained a slow, steady tension on the ropes. Any lapse in coordination could cause the sledge to halt or, worse, shift and settle unevenly. This system highlights the sophisticated project management inherent in these operations. It was not enough to have strong laborers. You needed foremen with acute spatial awareness, signalers to coordinate movement, and a clear chain of command to maintain the fragile momentum of the entire endeavor. The sound would have been a deep, rhythmic groaning of timber under immense pressure, the shuffle of hundreds of feet, and the shouted calls that kept the human machine in flawless sync. This was how a mountain learned to walk, not with a single heave, but through the cumulative power of countless small, perfectly timed actions, rolling its way into history. But a ramp of earth and a path of logs were only part of the solution. The real magic happened at the point of contact, in the thin, crucial layer between the massive sledge and the ground that refused to let it pass. This was the Lubrication Enigma, a battle against friction fought not with force but with ancient, intuitive science. Friction was the silent, invisible enemy, the force that multiplied the effort required 1,000-fold. To overcome it, ancient engineers turned to the most basic elements, transforming them into sophisticated tools. Water was likely the most common and readily available lubricant. Poured liberally ahead of the advancing sledge, it would mix with the soil of the ramp or road to create a slick, muddy slipway. This simple slurry drastically reduced the coefficient of friction, allowing the wooden runners to glide more freely. Think of how a wet sidewalk becomes perilously slippery, or how a child's water slide works. The ancients harnessed this same principle on a monumental scale, using teams of water carriers to constantly maintain the wet path ahead of the stone. But water could evaporate or soak away. For more demanding or longer hauls, evidence and experimentation suggest they may have used thicker substances. Animal fats rendered from livestock could provide a longer-lasting, greasy film. More intriguing are theories involving specially prepared clay slurries, mixtures of fine clay and water that created a viscous, almost plastic layer that supported weight while allowing movement. Some researchers have even proposed the use of liquid lime, a slurry of slaked lime, which would not only lubricate the path in the short term but could potentially harden over time into a smooth, plaster-like surface, effectively paving the way as they went. This attention to the microscopic interface reveals a profound, practical genius. They were engaged in applied physics long before the laws were formally written down. Their understanding came from observation and relentless trial and error. They learned that the right mixture could turn a Sisyphean struggle into a manageable, steady pull. The choice of lubricant would have been a critical logistical decision, factoring in distance, climate, and the weight of the stone. It underscores that moving these monoliths was not a single act of engineering, but a symphony of interconnected systems, each one solving a specific physical problem. The ramp provided the slope, the rollers distributed the weight, and the lubricant conquered the final, stubborn resistance of the earth itself. It was in this thin, wet layer of mud or grease that the theoretical became possible, where the dream of a moving mountain finally found its footing. The true engine behind every stone was not wood or water, but human will. While we marvel at the ingenious physics of ramps and rollers, the most complex system of all was the living, breathing one, the vast network of thousands of individuals organized with breathtaking efficiency. Moving a 1,000-ton block required more than a clever trick. It demanded a society capable of sustaining a monumental project for generations. This was an administrative and social feat that rivals the engineering, a testament to the immense political and economic power these civilizations could marshal. The workforce was a highly specialized ecosystem. At its foundation were the quarrymen, the masters of stone who could read the bedrock and wield dolerite pounders with rhythmic precision. Alongside them worked carpenters, crafting the massive sledges, wooden wedges, and intricate cribbing systems. Overseers and architects translated grand visions into daily tasks, their calculations dictating every cut and every pull. Then came the haulers, the vast teams who manned the ropes, their synchronized effort the direct physical translation of will into motion. Coordinating these diverse groups, ensuring that the quarry teams, the transport crews, and the construction site were all in perfect sync, was a logistical ballet of staggering complexity. How were such armies of labor assembled? The answer varies across cultures and reflects the social fabric of the time. In some cases, it was likely a form of conscripted labor, a duty owed to the state or the divine ruler, where citizens contributed a portion of their year to national projects. In others, it may have involved skilled artisans who passed their knowledge from father to son, creating a permanent, professional class of builders. Many projects also possessed a powerful communal or religious dimension, where participation was seen not as a burden, but as a sacred act that brought honor and spiritual benefit to the individual and their community. This distinction is crucial. It moves the narrative from one of mere coercion to one of shared purpose and cultural identity. The logistics of sustaining this human engine are almost as impressive as the stonework itself. Feeding thousands of workers required vast agricultural surplus and complex supply chains, bringing grain, fish, and beer from across the realm. Housing them meant building entire temporary cities near the quarry or construction site, complete with bakeries, breweries, and medical facilities. Administrative records from ancient Egypt, for instance, detail the issuance of rations, the organization of work gangs with descriptive names like the Powerful Ones, and even accounts of strikes over delayed payments of beer and bread, revealing a highly structured, bureaucratic system. This level of organization speaks to a civilization operating at its peak, capable of redirecting a significant portion of its wealth and manpower toward a single, enduring goal. The ability to mobilize, direct, and care for such a workforce for decades, even centuries, is perhaps the ultimate signature of a powerful state. It demonstrates control over resources, territory, and people, and a unifying vision powerful enough to coordinate the labor of generations. The silent stones, therefore, are not just monuments to kings or gods. They are monuments to the collective endeavor of an entire society, a frozen echo of the shouts, the chants, and the shared breath of thousands pulling as one. A single crack in the stone echoes louder than 1,000 perfect monuments. In the sun-baked quarries of Aswan, Egypt, the unfinished obelisk remains a profound testament to both staggering ambition and the razor-thin margin for error. This colossal shaft of pink granite, still partly fused to the bedrock, offers us a fossilized moment of ancient engineering in progress, a classroom of stone where we can walk among the very tools and techniques we have just explored. Had it been completed, it would have stretched over 100 feet into the sky and weighed an estimated 1,200 tons, dwarfing any other obelisk ever erected. Its story is not one of completion, but of a critical, instructive failure. The evidence is etched into the very fabric of the site. You can stand within the deep, narrow trenches that workers painstakingly carved to isolate the monolith, seeing the vertical walls shaped by countless dolerite pounders. You can trace the lines of rectangular slots cut along its sides, the precise homes for the wooden wedges that were meant to coax it free through hydraulic expansion. Every principle we have discussed is visible here, frozen in time. The quarry masters had successfully delineated the obelisk, executed the channeling, and likely employed thermal shock and wooden wedges. Yet, deep within the stone, a fatal flaw appeared, a large crack propagating through the granite. This fracture, likely a pre-existing weakness in the bedrock that was missed during the initial geological survey, or a stress fracture caused during the undercutting process, rendered the entire project worthless. In that moment, years of backbreaking labor, the coordinated effort of hundreds, perhaps thousands of workers, reached a sudden, absolute end. The obelisk was abandoned, left as a permanent monument to the limits of even the most advanced ancient technology. This failure, however, is what makes the site so priceless to our understanding. It shows us the risks they took with every single block. It underscores that their success was never guaranteed, that each monumental stone was a victory snatched from the very real possibility of catastrophe. The unfinished obelisk does not diminish their achievements, it humanizes them. It reminds us that these builders were not infallible magicians, but brilliant problem solvers working at the very edge of the possible, where nature held the final veto. When we look at the perfectly erected obelisks in Luxor or Rome, we should see not just their grandeur, but the silent, cracked twin in Aswan, the one that reminds us of the price of ambition and the incredible skill required to avoid such a fate. This single site transforms our awe into a deeper appreciation, framing every successful monolith as a triumph over immense and unforgiving odds. The crack in Aswan's obelisk reveals the high stakes of working at such a scale, but in another corner of the ancient world, the ambition grew even larger. At the sprawling complex of Baalbek in Lebanon, the Romans constructed a temple platform that seems to defy the very laws of physics. Here, the foundation stones themselves are the marvel, a trio of limestone behemoths known as the Trilithon. Each one is approximately 64 feet long, 14 feet high, and 12 feet deep, with a weight pushing 800 tons. To stand before them is to feel a profound sense of dislocation, as if the ordinary rules of construction have been suspended. These are not merely blocks, they are geological entities that have been persuaded to form a wall. Their surfaces are perfectly squared, their joints so tight that a razor blade cannot slip between them. They sit 20 feet above the ground, forming the base of the great temple of Jupiter. This placement creates the site's central, breathtaking mystery. How did they lift these giants so high? Quarry for these stones lies less than a mile away, and it holds an even more staggering clue. There, still partially embedded in the bedrock, rests the stone of the pregnant woman. This single block of limestone is estimated to weigh over 1,000 tons, making it one of the largest known worked stones from antiquity. It is a sleeping giant that never began its journey, a testament to a project that aimed for a scale we can barely comprehend. The presence of this quarry monster forces us to reconsider the entire operation at Baalbek. The challenges here were different from those in Aswan. While the Egyptians often moved stones over long, flat distances to the pyramid sites, the Roman engineers at Baalbek faced a critical vertical challenge after a relatively short horizontal haul. They had to elevate their 800-ton blocks to the top of a massive platform, a lift of about 20 feet. This changes the engineering puzzle dramatically. A simple, straight earthen ramp to lift a block of that weight to such a height would have been a mountain in its own right, requiring an unimaginable volume of fill material, more than the entire temple complex itself. So what did they do? The most plausible theories involve a combination of ingenuity and immense patience. One compelling idea is the use of a spiraling ramp, a gently sloping roadway that wrapped around the growing platform, allowing teams to pull the stones in a continuous, rising circuit. This would have reduced the slope to a manageable grade, though it would have extended the hauling distance many times over. another possibility is a sophisticated levering and cribbing system on a monumental scale. Imagine constructing a temporary stone or timber tower next to the platform. Using a complex arrangement of levers, pulleys, and counterweights, the block could be raised in stages, with cribbing inserted underneath each time it gained a few inches. This incremental lift, similar to how they raised stones from quarry pits but turned vertically, would have been a painstaking operation of precise coordination. The Romans were master engineers renowned for their concrete, arches, and cranes, but even their known technology seems stretched to its limits here. The sheer mass of the Baalbek stones pushes against the boundaries of what we believe was possible in the Roman era, leading some to wonder if they employed knowledge or techniques that have since been lost to history. The stone of the pregnant woman, forever waiting in its quarry, whispers of an even grander plan that was either abandoned or never initiated. Was it meant to be part of the platform or an even larger structure? Its very existence suggests that the Trilithon blocks were not the limit of their ambition, but merely what they successfully achieved. This site does not give up its secrets easily. Unlike the detailed tomb paintings of Egypt, we have no visual manual for Baalbek. We are left with the physical evidence, the stones themselves, and the empty space of the quarry. They force us to reconstruct the missing landscape of earth and timber, the shouts of foremen, and the groaning of ropes under impossible tension. The platform at Baalbek is not just a temple foundation. It is a silent lecture in advanced logistics, a permanent question carved in limestone that continues to challenge our understanding of the ancient world's capabilities. Yet the final test of mastery came not in moving the stone, but in its placement. The most breathtaking signature of ancient builders is found in the seams, the impossibly tight joints where one colossal block meets another. This is the mystery of the megalithic fit, a precision that seems to defy the tools of the time. At the fortress of Sacsayhuaman in Peru, towering zigzag walls are built from limestone boulders weighing up to 120 tons. These stones are not uniform rectangles, they are polygonal puzzles, each one a unique, irregular shape with multiple angles and curved faces. And yet, they fit together so perfectly that for centuries, locals said not even a single sheet of paper could be slipped between them. This same phenomenon appears thousands of miles away and centuries later at Coral Castle in Florida, where a single man, Edward Leedskalnin, secretly single-handedly quarried and fitted over 1,000 tons of coral rock. The precision of his joints is equally astonishing. How was such accuracy achieved with what we assume were simple tools? The answer lies in a secondary, patient art of fine dressing, a process that likely happened in situ, right at the construction site. After a stone was levered into its approximate position, the real work of customization began. The goal was to make the contact surfaces between two stones mirror each other with microscopic accuracy, creating a lock that distributed weight perfectly and made mortar unnecessary. One of the most effective methods involved a process of iterative grinding. Workers would use a softer stone, like sandstone, as a grinding tool, along with an abrasive slurry of sand and water. They would press the abrasive between the two rock faces and then move the new block back and forth, or in a rocking motion, against its neighbor. Each movement would grind away the high points on both stones simultaneously. They would check the fit repeatedly, marking contact points with pigment or soot, then grind again. Over days or weeks, this patient, reciprocal abrasion would create a conformal fit of extraordinary precision. It was a three-dimensional sanding process on a gargantuan scale. Some researchers have also proposed the use of chemical agents derived from local plants. Certain acidic plant juices, when applied to limestone or sandstone, could very slightly soften the surface, making it more amenable to shaping with abrasive grinding. This wouldn't melt the stone but could make the final fitting process less laborious. This on-site fine dressing explains the incredible variety of shapes. The builders were not cutting stones to a predetermined blueprint from a quarry. They were essentially sculpting the final connection in place, allowing each block to find its perfect mate in the wall. The result was a structural masterpiece. A dry stone wall with such tight joints is incredibly stable, as seismic energy from earthquakes is dissipated through the interlocking puzzle of stones, which can shift slightly without collapsing. This technique transformed a pile of massive rocks into a single, resilient monolith. The seamless joinery is the ultimate quiet boast of these ancient engineers, a testament to a philosophy where the journey was not complete until every last gap vanished, leaving only the silent, enduring pressure of stone against stone. The seamless joinery of these walls speaks of a profound intimacy with the material itself, a relationship forged not by overpowering force, but through the patient, repeated application of simple tools. This brings us to a critical re-evaluation of the very technology that made it all possible. To our modern eyes, the ancient toolkit appears almost shockingly basic. Dolerite pounders, copper chisels, wooden wedges, ropes of papyrus or hemp, and simple levers made of timber. We look at these objects and might be tempted to label them primitive, a word that carries an unspoken judgment of being crude or ineffective. But that label collapses under the weight of the evidence they left behind. These were not limitations, they were optimized solutions, each one perfectly adapted to the task, the material, and the human scale of the work. Experimental archaeology has been vital in shattering our misconceptions. Researchers have taken replicas of those dolerite pounders, the hard, fist-sized stones, and applied them to granite. The results are startling. With a skilled, rhythmic striking technique, a worker can fracture and remove granite at a rate that is far more efficient than most would assume. It is not about a single Herculean blow. It is about the cumulative effect of thousands of precisely placed impacts, a sustained percussion that turns solid rock into dust and manageable flakes. The copper chisel, often maligned for being soft, reveals its own genius when understood in context. Yes, it would dull and deform quickly against granite. But that very softness meant it could be easily resharpened or recast on site, using simple furnaces. It was a disposable, renewable cutting edge, perfect for fine dressing and detailed work where the stone pounder was too blunt an instrument. This toolkit was sustainable, crafted from locally available or easily produced materials. There were no complex supply chains for specialized alloy steel, no need for fossil fuels. The technology existed in a closed loop with the environment. The true sophistication was not in the individual tool, but in the orchestration. A master builder knew that the dolerite pounder started the fracture, the copper chisel refined the line, the wooden wedge expanded it with water, and the rope and lever provided the final persuasion. Each tool played its part in a sequence developed over generations. This forces a complete shift in perspective. We are not looking at a failed attempt at advanced technology. We are looking at a fully realized, brilliantly optimized system that leveraged human skill, natural physics, and profound patience. To call it primitive is to miss the point entirely. These builders achieved a harmony between their goals and their means, creating wonders not in spite of their tools, but because of the deep, mastered understanding of exactly what those tools could do. The real mystery then becomes not how they did it with so little, but how we lost such a comprehensive understanding of working in concert with our materials. The true genius of these ancient builders is revealed not in their defiance of nature, but in their profound collaboration with it. Water, the most common substance on Earth, became their most versatile and powerful tool, serving roles that modern engineers would need a warehouse of specialized equipment to replicate. In the quarry, water was the silent partner in the thermal shock process, the cold deluge that fractured granite after a fire's heat, but its duties did not end there. Mixed with fine sand or crushed stone, it created an abrasive slurry, a liquid sandpaper that allowed workers to grind and shape the hardest rock with nothing more than patient back and forth motion. This same slurry principle was likely used in the drilling of holes for levers or wedges, where a hollow reed or copper tube would be turned while sand and water were fed into it, slowly, relentlessly wearing a perfect cylindrical hole into solid stone. For transport, water transformed from a cutter into a lubricant and a highway. On land, poured ahead of the massive sledges, it turned earthen ramps into slick mudslides, reducing friction to a manageable minimum. But some of the most ambitious theories suggest they took this relationship to its logical extreme, using water not just to lubricate the path, but to become the path itself. In regions with seasonal floods like ancient Egypt, it is plausible that engineers dug canals directly to the base of quarry pits. During the annual inundation of the Nile, these pits would fill, transforming into temporary harbors. A prepared stone block, already secured to a barge or surrounded by buoyant materials like inflated animal skins, could then be floated from the quarry directly onto the rising floodwaters. This would turn the landscape itself into a hydraulic lifting system, using nature's own cycle to elevate and move colossal weights with an efficiency that ropes and ramps could never match. This holistic, systemic view of water showcases a mindset where every natural element was seen as a potential component in a larger machine. They did not just use resources, they integrated them into a seamless process. Water cooled, it cut, it carried, and it conveyed. This multifaceted approach is a quiet lesson in sustainable ingenuity, solving multiple monumental problems with a single, abundant, and free force of nature. It reflects a world where understanding the environment was the first and most critical step in reshaping it. The silent stones may hold an echo we can no longer hear. Beyond the physical tools of hammer and wedge lies a realm of more speculative yet utterly captivating theories, those involving the power of sound itself. Could ancient builders have used acoustic resonance or harmonic vibration as a tool to shape and move their monumental stones? While mainstream archaeology finds no direct, tangible evidence for such practices, the ideas persist, fueled by a potent combination of ancient legend and our own modern struggle to explain their staggering achievements. Stories from diverse cultures speak of a time when music or chant could command stone. Tibetan and Indian spiritual texts, for instance, describe the concept of acoustic levitation, where the correct sonic frequency could nullify gravity. Indigenous oral histories in the Americas sometimes reference sacred songs that guided the placement of great stones. These narratives are not historical records, but they point to a profound cultural memory, a lingering belief that sound was once a force of creation, not just art. Modern researchers exploring these concepts suggest that if a stone's natural resonant frequency could be identified and matched by a chorus of voices or a bank of tuned instruments, the resulting vibrations might reduce the effective weight of the block or alter the friction between it and the ground. On a smaller, observable scale, we know sound can influence matter. A powerful bass note can make a glass of water ripple, and an opera singer's sustained pitch can shatter a crystal glass by amplifying its vibrations to the breaking point. The leap to imagining this principle applied to a 1,000-ton block is vast, yet it speaks to a compelling human impulse. When faced with a feat that seems to defy every logical tool we can identify, we naturally reach for explanations that feel extraordinary. The acoustic theories, while scientifically unverified, serve a crucial purpose. They remind us that ancient knowledge systems were holistic, often blending the physical, spiritual, and cosmological into a single worldview. Their understanding of natural forces may have included intuitive grasps of wave physics and energy transfer that our own, more compartmentalized science is only beginning to formally explore and validate. These speculative ideas are less a blueprint for how it was done, and more a mirror reflecting our own enduring wonder. they challenge us to consider that the true toolkit of the ancients might have been even more sophisticated than we suppose, not in its complexity, but in its deep, integrated understanding of a universe where everything, even stone, has a song. The seamless fit of stone upon stone speaks of a knowledge so deep it feels instinctual, yet history whispers that such mastery is not guaranteed to endure. This precision confronts us with a haunting possibility, the lost knowledge hypothesis. Across the sweep of time, the techniques for working megalithic stone did not follow a simple, upward trajectory of improvement. Instead, they achieve staggering perfection, and then often fade, suggesting that specific, refined bodies of expertise were not simply passed down, but could be forgotten. Consider the Great Pyramid of Giza. Its original casing stones, fashioned from highly polished white Chora limestone, were cut with such accuracy that the joints between them were reportedly less than a millimeter wide. This created a surface so smooth it was said to gleam like a mirror under the sun. Yet, in the pyramids built by later pharaohs, even within the same civilization just centuries later, we do not see this same level of flawless joinery. The knowledge for that specific, exquisite finish seems to have diminished. This pattern repeats elsewhere. The monumental polygonal masonry of Sacsayhuaman has few direct successors in later Incan architecture, which often used smaller, more regularly shaped stones. So what happened? Was this knowledge held by a small, secretive guild of master builders, a closed circle of artisans who guarded their methods as sacred trust? Their techniques, refined over generations, might have been a blend of precise observation, ritual practice, and hands-on skill that was never fully written down, existing only in the minds and muscles of a select few. Furthermore, this expertise may have depended on a very specific social and economic structure to flourish. Creating a 1,000-ton block is not just an engineering challenge, it is a societal one. It requires the ability to command vast resources, organize thousands of workers, and sustain a project across decades. If that centralized power fractures, if the economic surplus dries up, or if a generation chooses to prioritize different goals, the entire delicate ecosystem that supports such monumental construction can collapse. The master builders may have had no apprentices, or their students may have never gotten the chance to practice on such a scale again. The knowledge without a project to apply it to could atrophy and dissolve within a single lifetime. This adds a profound layer of cultural mystery to the technical one. It forces us to ponder the fragility of human expertise. Our greatest achievements are not just carved in stone, they are carried in tradition, in practice, and in the continuity of purpose. A society can forget how to move mountains, not because it becomes less intelligent, but because the intricate web of conditions that made such a feat possible simply unravels. The silent stones, then, stand as monuments to a specific moment when knowledge, resources, and will aligned perfectly, a fleeting convergence that allowed humanity to touch the impossible before the tide of history quietly pulled that particular secret back out to sea. But could these methods actually work? The proof lies not just in the silent monuments, but in the sweat and strain of modern attempts to recreate them. To move beyond theory, teams of archaeologists and engineers have rolled up their sleeves, trading blueprints for ropes and levers to test these ancient techniques in the real world. One of the most famous demonstrations occurred in the 1990s, when a Japanese construction company partnered with Egyptologists to move a concrete replica of an Egyptian obelisk. Weighing a formidable 35 tons, far smaller than the ancient giants but still a massive object, it was a practical test of the sled and lubricated ramp theory. Using only materials available in antiquity, they built a large wooden sledge, laid a track of wooden rollers, and employed teams of volunteers on pulling ropes. Their most critical discovery was the effectiveness of the lubricant. They found that a simple mixture of water and clay, poured continuously ahead of the sledge, reduced the pulling force required by an astonishing amount. With this slick slurry, a team of around 100 people could move the obelisk at a steady pace. The experiment was a success, but it revealed the hidden complexities, the immense coordination needed to keep the rollers moving from back to front, the constant need for water carriers, and the sheer physical endurance required from every participant. It proved the physics were sound, but it also gave a visceral, human-scale appreciation for the monumental effort involved. Similarly, the Nova television series has conducted several landmark experiments over the years, including a project to raise a stone obelisk using a pivoting technique and a massive earthen ramp. These modern trials serve as a vital bridge between our speculative admiration and tangible understanding. They confirm that the ancient methods were not only possible, but were likely the most efficient means available. However, they also highlight a factor that blueprints can never capture: the intangible element of perfected practice. An ancient crew that had moved dozens of blocks would have developed an intuitive rhythm, a silent language of hand signals, and shared experience that a modern volunteer team, no matter how enthusiastic, could not instantly replicate. These experiments give us something invaluable: data. They measure the friction coefficients, the required pulling forces, and the time investment, translating awe into quantifiable facts. They silence skeptics who claim it could not have been done, while simultaneously humbling us with the scale of the ancient commitment. We see that the true machinery was not just wood and rope, but the synchronized will of a community, a force that leaves no fossil record but is written in the very possibility of the stone's journey. The allure of a mystery can sometimes eclipse the human story at its heart. When we stand before these impossible stones, a natural question whispers in our minds: how could people without power tools or engines possibly have done this? For some, the gap between our modern assumptions and their ancient achievement feels too vast to bridge with human ingenuity alone. This has given rise to popular narratives suggesting outside intervention, stories of lost high technology from a forgotten civilization, or even guidance from extraterrestrial visitors. These ideas capture the imagination, offering a shortcut to explain what seems inexplicable. They are compelling stories, but they share a common, subtle flaw. They begin from a place of underestimating our own ancestors. The real story, the one being pieced together by archaeologists and engineers, is not one of outside help, but of inside knowledge, a profound and hard-won understanding of the physical world. This human-centric explanation is in every way more impressive than any myth. It means that the people of the past were not passive recipients of advanced knowledge. They were active, brilliant problem solvers. They observed the way fire cracked rock, noticed how wood swelled with water, and understood how a lubricated path reduced friction. They then scaled these simple principles to a monumental degree through organization, patience, and generations of refined practice. The evidence for this is not hidden. It is written in the tool marks at the quarries, the abandoned sledges depicted in tomb paintings, and the successful modern experiments that replicate their methods using nothing but period-appropriate materials. To suggest they needed alien lasers or anti-gravity machines is to miss the true marvel, the sheer, inventive capability of the human mind when faced with a seemingly insurmountable challenge. The stones do not stand as proof of visitors from the stars. They stand as a testament to what human communities, working together with focused purpose, can literally move. By letting go of the extraterrestrial hypothesis, we do not diminish the wonder, we reclaim it for humanity. We see the fingerprints of the quarry master, the calloused hands of the hauler, and the sharp mind of the engineer in every perfectly fitted joint. The truth is remarkable enough on its own, a story of earth, water, wood, and will, orchestrated into monuments that continue to speak to us across the centuries. The legacy of these stones is written not only in the monuments they became, but in the very earth they left behind. Every quarry, from the vast pits of Aswan to the volcanic slopes of Rono Roroku, is a permanent transformation. These were not just extraction sites, they were landscapes of industry carved by human ambition into the bones of the planet. The once solid hillside became a negative space, a colossal open scar that would never heal. Over centuries, these quarries filled with rainwater became habitats for new life, or were slowly reclaimed by the elements, transforming from workplaces of immense noise and dust into silent, dramatic historical sites we visit today. This physical alteration was the first and most visible cost, a permanent exchange where a mountain gave a piece of itself to become a temple or a statue, forever changing the contour of its home. The ecological footprint extended far beyond the quarry's edge. The sheer scale of the supporting technology placed a tremendous demand on local resources, particularly one vital material, wood. Think of the thousands of wooden wedges needed to split a single monolith, each one swelling with water to exert its slow, powerful force. Consider the endless procession of logs required as rollers for a transport journey miles long, constantly cycled from back to front. Envision the massive sledges, the timber cribbing for lifting, and the framework for ramps. The consumption was staggering. For a civilization undertaking multiple monumental projects across generations, this could lead to significant regional deforestation. The forests that once surrounded a quarry might have been steadily cleared not for farmland, but to feed the endless appetite of construction. This could have altered local climates, affected water retention in soils, and displaced wildlife, creating an environmental ripple effect that lasted long after the last stone was set in place. This leads us to the profound social dimension, the human cost woven into the fabric of these achievements. We must consider the communities whose lives were irrevocably shaped by the stone. For generations, the rhythm of daily life in nearby villages would have been set by the demands of the quarry and the transport route. Fathers and sons might have spent their entire lives as part of a specialized work gang, their skills and identity tied to moving the unmovable. While some participation may have been a sacred duty or a source of pride, the sheer duration of these projects meant that countless individuals dedicated their labor, their health, and their years to a vision whose completion they might never witness. The social structure itself became an engineered system, meticulously organized to sustain this long-term effort, directing human energy as precisely as any lever-directed force. Adding this dimension of consequence does not diminish the brilliance of the engineering. It deepens our understanding of its true scale. It moves the story from a technical puzzle to a holistic human endeavor. The monuments stand not just as triumphs over physics, but as the culmination of complex relationships between people and their environment, between a society's ambition and its resources, between the sweat of a single worker and the enduring symbol of an entire culture. When we look at a polished granite obelisk or a seamless limestone wall, we are seeing only the final, silent product. The full story includes the altered hillside, the vanished forests, and the echoes of the generations who believed in something larger than themselves. Their legacy is a landscape forever changed, and a testament to what a civilization is willing to reshape, both in stone and in life, to create a mark meant to last for eternity. Granite in Egypt, andesite in the Andes, limestone in Lebanon, the stones differ, but the human response to their challenge sings a familiar, global chorus. When we place the quarrying techniques of these ancient cultures side by side, a remarkable pattern emerges, not of copied blueprints, but of convergent intellectual evolution. Isolated by continents and oceans, civilizations from the Nile Valley to the peaks of Peru arrived at eerily similar solutions for moving mountains, revealing a shared heritage of human ingenuity when faced with the same immutable laws of physics. Consider the foundational act of splitting stone. The Egyptians, masters of granite, harnessed thermal shock and wooden wedges swollen by water. Thousands of miles away, the Inca builders of Sacsayhuaman, working with volcanic andesite, also employed the wedge technique. Archaeologists have found precisely carved slots in their quarries at sites like Rumacolca, slots perfectly sized for wooden inserts that would expand with moisture to fracture the bedrock along clean lines. They did not need to trade secrets with pharaohs to understand that water could turn wood into a hydraulic jack. This parallel discovery speaks to a universal truth: observation of the natural world leads to powerful, repeatable innovations. Both cultures looked at a wet log, saw its expanding power, and realized it could be directed to perform Herculean labor. Yet within this convergence, beautiful divergences bloom, adaptations shaped by local material and vision. Egyptian granite, with its crystalline structure, often allowed for the extraction of enormous monolithic blocks like obelisks, prized for their smooth, imposing surfaces. Their work emphasized creating perfect, isolated giants from the earth. The Inca approach, particularly with their polygonal masonry, reflected a different relationship with stone. They often worked with andesite boulders already scattered by ancient geological forces, shaping them in situ into unique, interlocking puzzle pieces. Their genius was less about extracting a single perfect block and more about custom fitting each irregular stone to its neighbor through patient abrasion, creating walls that moved as a single, resilient entity during earthquakes. One culture sought to conquer the mountain with monumental uniformity, the other to collaborate with the landscape's inherent variety. The Romans, inheritors of both Greek and local Levantine knowledge at a place like Baalbek, showcase another facet of this global story: the drive to scale. While they utilized known principles of levering and ramp building, their ambition pushed the known limits of size, resulting in the 800-ton Trilithon blocks. This reflects a cultural moment where immense imperial resources and engineering confidence converged, applying established techniques to a new, staggering magnitude. It was not a new invention, but a bold amplification of an old idea, proving that the same basic physics could be asked to perform ever more audacious feats when supported by vast organization. This comparative view dismantles the idea of a single, lost super-civilization seeding knowledge across the globe. Instead, it paints a far more inspiring picture: multiple cultures working independently, hitting upon the same elegant solutions because the problems and the material properties of wood, water, and stone were constants. Gravity feels the same in Cusco as it does in Cairo. Friction obeys the same rules on a Peruvian slope as on an Egyptian plain. When human need meets a universal physical constraint, the spectrum of possible solutions narrows, and brilliant minds, separated by time and space, often arrive at the same destination. This is not evidence of contact, but of the shared cognitive toolkit of our species, a testament to our innate capacity for observation, experimentation, and profound mechanical creativity. The silent quarries of the world are not isolated mysteries. They are individual verses in a common epic of human problem-solving, written in the language of stone. These stones are far more than inert material. They are profound cultural statements, frozen in the very moment of their creation. When we decipher the language of their extraction and movement, we are not just reading a technical manual, we are listening to the values and the world-view of the people who commanded them. The most immediate message is one of breathtaking, generational patience. A single obelisk or foundation block could represent a decade or more of sustained labor. This means the architect who drew the first line in the quarry dust would almost certainly never see his work completed and placed. The workers who pounded the first dolerite hammer would grow old and pass on, their sons and perhaps their grandsons taking up the same tools to finish the task. This required a civilization with a radically different relationship to time than our own, one that could hold a vision steady across the span of many human lifetimes. It speaks of a society so confident in its continuity, so certain of its purpose, that it could invest irreplaceable resources in a project whose full glory would only be revealed to future generations. This was not a short-term calculation. It was an act of faith in the enduring power of their culture, a deliberate handshake with posterity. The sheer scale of coordination tells another story. To marshal thousands of specialists, quarrymen, carpenters, haulers, water bearers, overseers, and synchronize their efforts for years on end requires a highly structured, hierarchical society. There had to be clear chains of command, systems for rationing food and supplies, and methods for resolving disputes. This level of organization implies a powerful central authority, whether a pharaoh, an emperor, or a theocratic state, capable of mobilizing a significant portion of its population toward a single, symbolic goal. Yet, within that hierarchy, there is also evidence of remarkable collective effort. The tomb painting of the Colossus being pulled shows not slaves under a whip, but organized teams moving in rhythm, a figure pouring lubricant to ease their burden. This hints that the labor, while undoubtedly demanding, may have been framed within a shared cultural or spiritual endeavor. Participating in raising a temple or a memorial could have been seen as a sacred duty, an act that brought honor to one's community and favor from the gods. The stone itself becomes a testament to social cohesion, a physical manifestation of what a society can achieve when it moves, literally, in one direction. Underpinning all of this was a deep, empirical wisdom. Their knowledge was not theoretical, it was earned through relentless observation and hands-on experimentation. They knew which granite bed was flawless, how much water would make a clay slurry perfectly slick, and exactly where to place a wooden wedge to guide a fracture. This was science in its most practical and potent form, a dialogue with the natural world where they learned to work with physics, not against it. They listened to the stone, understood the swelling of wood, and harnessed the power of water in 3 different states, as a liquid lubricant, a solid expanding force in ice, and a gaseous agent in steam from thermal shock. This reflects a world view where humanity was not separate from nature, but an active participant within it, using intelligence to collaborate with elemental forces toward a grand design. Finally, the choice of such permanent, indestructible material speaks to a drive that transcends the practical. They did not build in wood or mud brick for these core monuments. They chose granite, basalt, and limestone materials meant to defy the centuries. This was a statement aimed at eternity. Whether to honor a god, glorify a ruler, or anchor a community's identity to a specific place, these stones were an attempt to carve a piece of the present into the endless flow of future time. The techniques of quarrying and moving them, therefore, are not mere steps in a construction manual. They are the physical expression of cultural values, perseverance in the face of impossible tasks, collective effort over individual glory, and a profound, intelligent dialogue with the very substance of the world. The true legacy is not just in the shape of the stone, but in the enduring echo of the mindset that dared to move it. The silent quarries and towering walls are not merely relics of forgotten labor. They are permanent signatures of human ingenuity, a language written in the language of earth, water, and stone. We have traced the journey from the moment a master builder read the subtle grain of the bedrock to the final, seamless placement of a 1,000-ton block. We have seen fire and water conspire to fracture granite, watched as wooden wedges swelled with patient hydraulic force, and felt the imagined strain of ropes as teams guided a stone along a slickened ramp. While questions linger at the edges of our understanding, the overwhelming evidence sings a clear and powerful chorus. The most extraordinary force at work was not magic, nor was it handed down from beyond the stars. It was the focused, collective will of people who looked at a mountain and saw not an obstacle but a partner. Their true toolkit was a profound observation of the natural world, an innovative spirit that turned simple materials into elegant solutions, and a determination that could span generations. These monuments stand as a timeless reminder that the boundaries of what is possible are rarely set by the tools in our hands, but by the breadth of our imagination and the depth of our resolve. They challenge us to look at our own seemingly impossible tasks not with doubt, but with the knowledge that human creativity, when united by purpose, can move literal mountains. If this journey into ancient genius resonated with you, we would love to hear your perspective. Which of these techniques left you most in awe of our ancestors' capabilities? Share your thoughts in the comments below, and subscribe to join us as we continue to unravel the profound mysteries woven into the fabric of our shared history. Thank you for watching.